Yes, if you have any questions, please let me know. Today we have repetition. We repeat different tasks from previous exams, and we don't have lecture today. Okay, everything is ready and we can start. So let me start with first task, and we discuss task number 1 from exam from 24th February of 2016. And there we have the following task. We have deterministic aperiodic signal, and we're given this expression for this signal, and we need to draw the signal itself. We need to determine energy of the signal, find out the correlation function, and taking into account that we have only one realization of the signal. Then we say that this signal is, we repeat it periodically, and we need to again find another autocorrelation function that corresponds to periodic signal. So let's start this task, and our task number 1. So the signal given by the following expression, we have sum of 3 parts and goes from, 4 parts and goes from 0 to 3, n times rectangular pulse, and for each part we have different shift in time domain. T minus n capital T minus T over 2 divided by capital T. given with such signal. And also we know that amplitude A0 up to value L3 belongs to the alphabet 1, 1, 1, minus 1. I would say it's not alphabet, but it's values have amplitudes, because order matters. We cannot just take randomly, order matters, and we have such series of amplitudes. So first part that we need to solve for this task, we need to draw the signal x of t. We have 4 intervals, and if we look to our rectangular pulse, we notice that it's nothing else as pulse centered at t/2. Yeah, if we set n equals to 0, it will be centered at t/2. So we can denote that this is our range from 0 to capital T. And pulse will be centered at t/2, and amplitude will be A0. A0 is 1. So this is our first pulse. If we set n equals to 1, then we have t/2 minus t/2 minus t. It will be minus 3t/2. It will be there. And we have this is the middle of rectangular pulse with width capital T, and amplitude will be 1. So we have second rectangular pulse that we can draw third one, and for the last rectangular pulse we have amplitude minus 1. So this is how our signal would look like. And now we can go to part B. At part B, we need to determine the system theoretic energy of the signal. And we can say that energy is nothing else as integral of our signal from minus infinity to infinity, x of t squared dt. And we can replace this integral by summation. We can calculate summation. I goes from 0 to 3, ai squared times t, duration of each pulse. And for this case, we see that it equals to 4t, because each amplitude has magnitude 1. Each pulse has magnitude 1. So then we go to part C. We need to draw the corresponding autocorrelation function for this finite series of pulses. And we can do this by we can calculate it, and we just need to find what happens for different shifts, because you remember that this signal we can represent as convolution. X of t equals to rectangular pulse t minus t/2 divided by t, convolved with and then we have this summation. I goes from 0 to 3, ai times, or I should write n instead of I, an, and times the delta pulse. We have tau minus n capital T. And in order to find convolution, in order to find autocorrelation for x of t, we need to find autocorrelation for pulse shape function. We need to find autocorrelation for this sequence of delta pulses. And then we calculate resulting convolution a resulting autocorrelation function as convolution between two autocorrelation functions. So let's find the autocorrelation function for this part that we can denote as x delta. No, delta t, not x delta, as delta t. And as far as it's just a sequence of delta pulses, we need to analyze what happens for different discrete delays rather than for all continuous range of values for delay. So original sequence will be 1, 1, 1, minus 1. And we have first option for delay equals to 0, another option t, 2t, and 3t. And then actually our autocorrelation will be equal to 0 because original signal and shifted version will not overlap because the whole duration of our signal is 4t. So then for 0 delay, I just repeat the same sequence. And in order to find the sum or autocorrelation for 0 delay, I need to element-wise multiply elements of two sequences above and below and calculate sum of resulting products. It gives me result 4. Then if I shift by 1, period, by capital T, my sequence will be 1, 1, minus 1, and 0, because when we shift, we don't have anything on the right side. So we just add extra zeros. And again, if we multiply original sequence with this delayed version and calculate sum, we see that the result will be 1 plus 1 minus 1 plus 0. It will equal 1. For, yeah, let's do another shift. 1 minus 1 is 0, 0. And the result will give us 0. And for the last shift, we see that the product and summation gives us result minus 1. So now we have points for discrete autocorrelation function. And we remember that in order to find resulting autocorrelation function, we need to calculate convolution between autocorrelation function for pulse shape. And in our case, we have rectangular pulse, and we know that for rectangular pulse, autocorrelation will be triangular function. And in this case, it goes from minus t to capital T. And amplitude will be energy of rectangular pulse. So it will be 1 times t. Capital T is maximum value times, sorry, not times, but convolution with discrete autocorrelation function. This autocorrelation for delta t. And at 0, we have value 4. At capital T and minus capital T, we have value 1. One second, we don't have discrete pulses, but we have delta pulses. We have delta pulses, and then we have for the remaining parts, we have 0, 0, and minus 1. Magnitude minus 1. 1, minus 1. T, 2t, minus t, minus 2t, and then minus 3t, and so on. This is delay. And if we calculate this convolution, I will increase size because otherwise it's too shallow. So it in the middle. And now actually we need to find resulting autocorrelation. It might be not obvious how the resulting autocorrelation will look like. For this reason, at the beginning, I will show you so in the middle we have the largest part, this triangular function. Then at capital T, we have another triangular function, and at minus capital T. Then at 2t, we have nothing, and at minus 3t and minus 3t and plus 3t, we have minus triangle. So now you see all components. And in order to find the resulting autocorrelation, you need to calculate sum of all of them. As far as working with linear functions, it's very easy to calculate if you just connect points for all triangulars. So we have the following behavior for our autocorrelation function. For our resulting autocorrelation function. So as the maximum, it will have value for capital T, this autocorrelation function for x of tau. Then we have capital T, 2t, 3t, 4t. Yeah. And afterwards, it will be 0. Because we have finite duration for our signal. So this is how our autocorrelation function will look like. And that is what we have for part C. Okay, if you have any questions, you are welcome to write in the chat. And we go to next part. So then we assume that our signal xt transmitted periodically. And the periodic signal can be written as yp of t this periodic signal equals to summation k goes from minus infinity to infinity xt minus small k for capital T. This is how periodic version looks like. And draw the corresponding autocorrelation function phi y of p of tau. And we need to remember that our signal is periodic. In order to better understand how it works, I would propose to make just plot how the signal looks like. But plot it I would say just without too much notations, just show that how this periodic version might look like for our signal. So, and it goes from minus infinity to plus infinity. This is our signal yp of t in time domain, and this period equals to 4 capital T what else? And now we need to find autocorrelation function. This is question D. And we use the same idea as before. You can represent even if we have periodic signal, we can represent it as convolution We can even say we can represent it as this double convolution. Yeah, we can say that our signal yp of t is nothing else as x, or what was the, no, not x, but rectangular shape function. T minus capital T over 2 divided by capital T. Convolution with second part, summation, n goes from 0 to 3, an times delta t minus n capital T. But in addition, we have another convolution. Summation k goes from minus infinity to infinity. Delta pulse t minus k for capital T. This is period of our sequence. But in order to find autocorrelation, we use all the same steps that we did before. First, we can find autocorrelation, as we already know it, for pulse shape. We can find autocorrelation for the whole sequence, periodic sequence, and then combine these two parts. Calculate convolution. So, and again, we need to find calculate table for all possible shifts. So let's do this, and actually we're going to calculate, first we calculate autocorrelation for discrete sequence of, for periodic sequence of symbols in discrete time, and then we extend it for continuous time. So we say that we have this sequence. We can calculate okay, we can just calculate it directly. So here I show what's the shift between, what's the shift in integer number of samples. Then I write my original sequence, 1, 1, 1, 1, 1, minus 1. And in the end, I write summation. And also remember that when we calculate the autocorrelation for periodic signal, we normalize by, in discrete time, we normalize by number of samples. So we have expression here, but I think it's not right. It's not. Okay, let me write it. I will say z in discrete time, function of m, and then we write it as 1 over n times summation, n goes from 0 to 3 in our case, and we have an times an plus n. So, and I mean, this is just one example. Of course, in general, there are many different ways how we can find it, no restrictions. So, and then I just show that we have shift for 0 samples, 1 sample, 2 samples, 3 samples. So then we have 1, 1, 1, minus 1. This is 4. No shift between copies. And if we calculate element-wise product and then we divide by number of samples, we have 1. Then we have 1, 1, minus 1. And previously we put 0, but now we put 1 because we have a sample from another period, from next period. And if we calculate element-wise product and summation, we see we have 1 plus 1 minus 1 minus 1. Result will be equal to 0. And for all other shifts, result will be equal to 0. Minus 1, 1, 1, 1. So we see that we have only one non-zero value. And in addition, this autocorrelation will be periodic, because if I calculate for shift number 4, we have sequence 1, 1, 1, and minus 1. And if we calculate element-wise product and calculate sum, it gives us 1. And of course, we divide by number of samples, 4 samples in one period. So, and as a result, this was it was autocorrelation for discrete time. When we extend it for continuous time, we have to normalize by by spacing between delta pulses. And remember that in our case, we have spacing 4t, and we have to take this into account when we calculate autocorrelation. So now I show that we have original autocorrelation for pulse shape. It was triangular function that goes from minus t to capital T, and value goes capital T, pi of tau. Then we have tau for x-axis. Then we calculate convolution with no, we don't have enough space. One, two, three, four. Actually, I think maybe in order to avoid confusion, maybe we remove this, and here we just write 4, and then when we normalize, so we get the result as it should be. Okay, so we have delta pulse at 0, then we have minus t, 2t, another delta pulse at minus 4t and 4t, and value will be equal to 1 over t, because we take this value 4 and divide by spacing 4t. So as a result, we get that our resulting autocorrelation for the periodic version of the signal will be equal, and then we have triangular pulse. We replace each delta pulse with a triangular pulse. And the resulting amplitude should be 1. So, I think the last question, we need to draw the power spectrum density. We need to draw the power spectrum density, part E, and we can simply calculate it if we yeah, but we can calculate it, but first maybe we should write autocorrelation function. Oops, it's not delta, it should be y of b. If we write expression for autocorrelation function, if we formalize it, and we can write it as triangular function tau over capital T, convolved with sequence of delta pulses. Say k equals to minus infinity to infinity, delta pulse tau minus 4 capital T. Now we calculate power spectral density. And for triangular pulse shape, we have T times C square function pi f capital T times, and for the sequence of delta pulses, we have 1 over 4t times summation mu goes from minus infinity to infinity. And we have for delta pulse, we have another sequence of delta pulses. For this reason, we have different index. Instead of k, we have index mu. F minus 1 over 4t. 1 over 4t. And now we can simplify this expression. We can cancel capital T. And we get the resulting expression for power spectral density. 1 over 4 times c square function pi f capital T times summation mu goes to minus infinity. Delta pulses f minus 1 over, and I forget to place, of course, index. F minus mu times 1 over 4 capital T. So this is how the resulting expression looks like. So that's all for the first task. Not almost all, because at the very end, we have to also plot this power spectral density.
Professor?
Yes, other questions?
Yes. While formulating the autocorrelation function of y of p, is it like triangular of t by tau convolution with delta pulse of the below only there? The question E. Is it delta tau minus 4 kt?
Question B.
Question E, not B, E.
Yes. Which part?
The delta pulse. Is it tau minus 4 kt or?
Of course, yeah, of course, there should be index. Yeah, thank you for noticing this, because if we don't place index, we have only one delta pulse. Yes, also K should be there, as well as mu for frequency domain. Thank you for noticing this, and yeah, the final part, we need to plot this power spectral density. So let's denote let's do it wider. So, and first we start this C square function. That's how C square function looks like approximately. Remember, it's smooth. You don't have very sharp changes, very smooth function. And the maximum value should be 1/4. And we have to sample this function with period 1/4 in frequency domain. And I put corresponding delta pulses. So the blue line corresponds to envelope, but we don't have such envelope. What we have weighted sequence of delta pulses. This is purple that I show with this purple color. And we could show this envelope with dashed line, because it just specifies what will be the magnitude of each delta pulse in this unfinite sequence. So, and here we see that it's spacing between delta pulses 1/4t. Nulls located at capital T and minus capital T, and then multiples of this value, 2t, 3t, and so on. And the maximum value 1/4. This is power spectral density for our periodic signal. And because it's periodic, we have discrete power spectral density. And now that's all for our first task for today. Now we can go to the next task. It is task. Yes. Another question.
Yeah, I'm sorry. Like the cuts in the graph should be when it goes to 0, 1 divided by t, and the second one is 1, like 2 divided by t, right? It's not t and 2t.
Ah, yes, of course.
Because we are in
frequency. Yes, thank you. Yeah, you're right. It should be 1/capital T and 2/capital T. Yeah, because we in frequency domain. Yes, it's a good point. Very good point. Yes, yeah. I hope I didn't make more typos. Oh, and it's not time, it's frequency. Yes. Yeah. Sorry, and I think now it should be right. Okay, so let's go to the next task, and we have task from 2015. From 24th of September. So for this task, we consider a White-Sand stationary process with given autocorrelation function. Autocorrelation function is given. It can be written as phi xx of tau equals to u0 squared over 4 plus u0 squared over 4 times triangular shape function tau over capital T. minus u0 squared over 8 times, and then inside parentheses we have sum of two triangular functions. We have triangular tau minus capital T divided by T, and plus another triangular function tau plus capital T divided by capital T. So this is how the question function looks like. And also for this question, we have multiple subtasks. We need to draw the figure, we need to specify the second moment, write what might be the values for the first moment, and we need to determine Pascal density of the function. So we start with the first part. So we need to draw this autocorrelation function for A. So we have delay axis. And first we start with placing DC component, or this constant component, in our autocorrelation function. So we have u0 squared over 4, it's DC part, and maybe I use orange line to represent this constant part in our autocorrelation function. Oh no, maybe it's better if I use gray for all values, and then I show with red the resulting autocorrelation function. So second part that we have at the origin we have triangular function which goes from minus t to capital T. So, and we can say that this is length that corresponds to, or this is the points where we have delay minus t and capital T. And original amplitude was for DC component u0 divided by 4. And I can simply place this triangular in this blue circle above DC component, because of course they come together. Yeah, we have DC plus additional part at origin. On top of this DC component, we have this triangular. There is another additional amplitude, u0 squared over 4. Okay, then we go to points minus t and capital T, because at these points we have two triangulars, both of them with negative amplitude. So I will use as baseline this DC part, this constant, and I show that actually our yeah, maybe I use more space. To make it better. This is what we have at 0, and then we have at minus capital T and at capital T, we have two triangulars with negative amplitudes. I show these triangulars respect to baseline that we have represented by this gray line. So because we have this baseline minus triangle, and this is what you see here. And now we need to connect all dots and show how the resulting autocorrelation function will look like. So at minus infinity, we have constant value. At minus 2t, we have the last point when the value is constant. At minus t, amplitude will be, it will be u0 squared over 8. And then at origin, amplitude will be u0 squared over 2. And then for the right part, we have just a flipped version of what we have at negative delays. And I can show the resulting autocorrelation function by just connecting dots, because in between dots, everything is linear. And if we calculate, we can just get point on this line connecting dots. So with this red line, you see how the resulting autocorrelation function will look like. So the maximum value will be u0 squared over 2. Minimum value will correspond to u0 squared over 8. And this value at edges will be u0 squared over 4. This is how our autocorrelation function looks like. Then we need to find second moment of the random signal. So we have only information about autocorrelation function, but based on it, we can find what's the second moment. Because you remember that if you take autocorrelation function and calculate or find value at 0 for 0 delay, this value corresponds to second moment, to variance of your random process. And we can say that second moment is nothing else as autocorrelation function at 0, and it equals to u0 squared over 2. On the other side, when we calculate, or if we want to calculate first moment, we can notice that if we take a delay large enough, so that the two sequences will be uncorrelated, the point at limit when the delay is very large corresponds to squared value of first moment. So we can say that first moment squared is nothing else as the limit when tau goes to infinity of our autocorrelation function. Simply speaking, if you take something on for very large delays, then this point corresponds to squared value of first moment. And as a result, you can say that first moment itself of this, other way around, of this random process, we can find as square root from autocorrelation function when tau goes to infinity. And here we have delay is constant and equals to u0 squared over 4 at limit. And as a result, first moment, we can say that first moment equals to u0 plus minus u0 over 2. These are two possible values for the first moment of the autocorrelation process function. And the last question, that we need to determine the equation of the power spectral density and simplify the result by means of the addition. Yeah, and we have some hint in order to calculate the result. So we say that sine square of x can be written as 1 over 2, 1 minus cosine 2x. This is the hint that we can use. And in order to find power spectral density, we simply need to calculate Fourier transform for our original autocorrelation function. So let's do it step by step. So we have f x of f, y of x of f, and we just do it for each term separately. First part is a constant, and if we calculate Fourier transform, we get the same amplitude, but they're located at origin. So times delta pulse of f. Then for second term in our autocorrelation function, It's simply a Fourier transform of the triangular function, and it gives us u0 squared over 4 times capital T times c squared function pi f capital T minus, and second part, for simplicity, we can actually rewrite it in slightly different form. We can write it as u0 squared over 8 times triangular no, I would say we write it as u0 squared over 4 times triangular function tau over capital T, convolve it with the following expression, 1 over 2 delta pulse. Then we have delta pulse tau minus capital T, and plus 1 over 2 delta pulse tau plus capital T. And then, of course, this after Fourier transform, this convolution will be converted to product, and we get that we have u0 squared over 4 times capital T, c squared pi f capital T. I should change color. Times, and inside parentheses, it is nothing else as cosine, right? Remember, if you have sum of two delta pulses with half of amplitude each, the resulting convolution, the transform will give us cosine. But in this case, we have cosine in frequency domain times cosine 2 pi f capital T. This is how it looks like. And now what we can do further, if we move outside parentheses, u0 squared over 4 times t times c squared from last two terms, inside parentheses, we will have 1 over cosine 2 pi f capital T, which is nothing else, if we use hint above, as 2 times sine squared pi f capital T. And it helps us to rewrite our expression and get the final result that we have u0 squared over 4 times delta pulse at origin plus u0 squared over 4 times capital T times c squared pi f capital T times 2. Maybe we can cancel 2 immediately and write scale in front of it as u0 squared over 2 times sine squared pi f capital T. So this is the final result that we get. This is Paustick density that corresponds to this autocorrelation function. Okay, let's go further, and we can go to task number 3. For today. And this task from exam from 2013. Okay, we have the following task. By means of a delay interferometer, it is possible to convert an antipodal signal S1 of t into the so-called dual binary signal S2 of t. And then we have expression for antipodal signal S1 of t. So S1 of t given as basis function psi1 times square root of E of b times n equals times summation, and it goes from minus into infinity, z of n times delta t minus n capital T of b, and we have this sequence of random bits, random symbols, and the basis function for this example given as rectangular shaped function t minus tb over 6 divided by tb over 3. So, and also, no, we simply know that tb is time interval of one symbol, and we know that sequence of transmit symbols z of n belongs to the alphabet from -1 that includes values -1 and 1. So also we say that EB is the mean energy per bit. Mean energy per bit. And first of all, we need to determine constant K in front of basis function in order to ensure a unit energy of the basis function. So part A, what's the value for constant K? So we say that energy for basis function, which equals to integral from 0 to tb of this basis function squared over time, and that in our case it will be equal to amplitude squared times duration of pulse tb over 3. This product must be equal to 1, must be unit energy. From where we can see that K equals to 3 over tb under square root. This is the value for amplitude K, and we can show how the basis function will look like. So impulse, non-zero impulse goes from 0 to capital T over capital TB over 3, and it has amplitude 3 over TB under square root, and for the remaining two intervals it equals to 0. So this is how our basis function looks like, and we also have amplitude for it. Then for part B, we need to find autocorrelation function for this basis function. So we need to find autocorrelation of the basis function. And we know that it's not periodic, it's just finite basis function that goes from 0 to capital TB. And it has only one non-zero interval from 0 to TB over 3. And actually we can treat this basis function as just a pulse that goes from 0 to capital TB over 3. And we already know what's the autocorrelation function if we have only one pulse. It will be a triangular function. So this autocorrelation function is just triangular shape function that goes from minus TB over 3 to TB over 3. And it has amplitude 1, because this is a normalized basis function. and energy for it equals to 1. Okay. Next part, we need to say what's the autocorrelation function of part S of D. And S of D is everything what we have on the right side for our original signal. SD of T, this discrete part of our signal. We need to find what the autocorrelation function for this discrete part. And of course, as we did before, in order to do this, we can say that first of all, we calculate autocorrelation, discrete autocorrelation function for sequence 0, n, and then we normalize it by duration of one symbol, which is TB, and it helps us to find the resulting autocorrelation function for this discrete sequence. And of course, we also should multiply by square root of ED. So let's do this and part C. So we say that this autocorrelation function for different delays we can find. And by the way, we also say that adjacent symbols are independent, and as a result, we can say that autocorrelation function we can find if L equals to 0 as second moment, and first moment squared if L not equal to 0. And as a result, as far as our sequence contains only values -1 and 1, if we calculate square value, it will be a sequence of ones, and as a result, that second moment will be equal to 1 for when L equals to 0. And if we say that they're independent, we have the same probability for -1 and 1, and it means that if we calculate mean value, it will be equal to 0. It will be -1 times 1/2 probability for -1 plus 1 multiplied by 1/2. As a result, it will be equal to 0. L non equals to 0. And as a result, we get that our autocorrelation function, discrete autocorrelation function, is just a discrete pulse at origin, and for all other delays, the result equals to 0. 1, 2, -1, -2. This is delay in samples. And if we normalize this autocorrelation function by duration of a symbol, then we can find how the autocorrelation function of this discrete sequence of weighted delta pulses will look like. I will show the result. That we have normalized delta pulse with magnitude 1/TB, and at 0, and for all other delays in time, we have 0. This is autocorrelation function of SD of tau. And then we can calculate the autocorrelation function with pulse shape autocorrelation function and find how the resulting autocorrelation function of the whole sequence of symbols will look like. So it was triangular function centered at origin, and that goes from -TB/3 to TB/3. And what was the amplitude? Amplitude was 1. So psi1 of tau energy. As a result, we just need to replace delta pulse by this triangular shape function and normalize amplitude. So result will be triangular shape function that goes from minus TB over 3 to TB over 3 and with amplitude 1 over TB. Over TB. Then we can write, so this is pi, signal was S1, S1 tau, and it was delay. So now we can write how this autocorrelation function can be written 1 over TB times triangular function tau divided by TB over 3, which is duration of our triangular function.
Professor,
Yes?
just one question. In the autocorrelation of the S0, do we need to add the square root of the energy of the bit? I mean, it's
Yes.
an additional.
Oh, it's a good point. It's a very good point. Yes, thank you, because I forget that we have also this scalar in front of it.
Yeah.
Yes, you're absolutely right. And but it won't be square root. It will be EB. Yeah, it will be EB because when you calculate autocorrelation, you calculate product. And this square root of EB will come as part of each component when we calculate autocorrelation. It's absolutely right. We have additional EB part, EB, and then as a result we have EB. Yeah, you see that it's very easy to get scalars, and we also put EB in our result expression. So it will be energy per bit divided by duration of our signal. Absolutely right. And now we can find how the power spectrum density will look like. So we have pi S1 of F, and this is simply triangular shape function. So we have EB over TB times TB over 3, because this is duration of our triangular function, times C square function pi F times TB over 3. This is how it looks like, and we can cancel TB and TB, and result will be equal to EB over 3 times C square function by F TB over 3. So this is how it looks like. And this is the final result for this question. Okay, are there any questions?
Just go to the starting section of this question.
Yes, and what's the question?
Just push your screen above. Yeah. Okay.
Sir,
Yes,
I have
welcome.
a question. Like, how did we calculate this second moment as 1?
We calculated second moment as 1, just following, if you remember, that's definition of second moment. Of, was it? Yeah, it was no, x dot z. mz second moment. The definition is the following, that you just take summation
Infinity
over
to
all, sorry?
minus infinity to plus infinity? Or maybe it is
I
different.
would say for over all possible values, because we're talking about discrete alphabet, we should take all possible values starting from 1 to k times z. How should we denote it? Okay, z n I would say this ith element from alphabet squared times probability of ith component,
Mhm.
like this. And if you plug what we know about our sequence, we have only two values. We have -1 squared times probability. This is for first element in alphabet, 1 or 2, plus 1 squared times 1 over 2. And you see that for first part, we have
Mm.
1/2.
Yeah.
For the second part, we have also 1/2. And if you calculate sum of two parts, it gives you 1.
Yeah.
But actually, it's absolutely natural, because if you look to arbitrary sequence, just like sequence of ones and -1s,
Mm.
this is original sequence, just random sequence you have. But in general, the number, actually, that even doesn't matter what's the number of -1 and 1s. This is your original sequence, let's say z of n, as function of n. Then you calculate square value. Yeah, but what's important is that you have amplitude 1. You calculate square value, z of n squared. And after you calculate square value, all of them will have the same amplitude.
Okay.
Because if it had amplitude -1 before, after you calculate the square value, it will be 1. And then second moment tells you, just calculate mean value of squared sequence. And then what will be the mean value if you have sequence of only ones? It is 1. It is 1, and this is natural explanation why, if you have this binary sequence, after calculating second moment, if you have binary sequence with amplitude -1 and 1, why after calculating second moment you get just value 1? Because all of these components will have the same amplitude.
Okay. So in the question itself, it is mentioned that this is binary.
Yes, it's mentioned because in the beginning we say that alphabet given by
Right.
only two values. Yeah, it's yes, it's given, and this is what we know about sequence, that we have only two values, -1 and 1. But you should also be careful if you have different alphabet, because if I think it was the last seminar we had sequence 0 and 1, and for this case, if both alphabets have the same probability, then the resulting value for second moment will be, as I remember, it was 1/2.
Okay.
It was correct. But I mean, you're right that there is no reason why it should be 1 in general, but for this specific case, it is true. It is true for this specific case, but in general, you should check it and calculate it explicitly. For example, using this way, as I have shown in green.
Okay. Sir, I didn't find this 2013 paper in sample exams.
It might happen, that, but it's not a problem, because then you have more tasks.
Okay.
Yeah, I mean, because I have some set of exams that I would like to discuss, but yeah, I was not sure that if you have it, but it's not a problem. Then you have just extra tasks that. But then you can also, of course, you can solve tasks from provided exams, and for you, I think it will be even better for you.
Is it hello?
Yes, I can hear you.
Is it possible to share the question, because otherwise it gets difficult to understand later? The 2013 one.
But what's the difficult part? I could try to explain you right now.
No,
The
not in
idea
that.
was, yes.
No, not in that way. I meant the question. If the question stays, then we can see refer later. That's what I meant. The other papers are there in Moodle, so we can like see later and understand. So that's why.
Yeah, I mean, it could be, we can try to share, but I cannot do it right now. But in general, it's possible, of course. But nonetheless, I mean, I hope that it should be clear what the question about. That you have signal that given in this form, it is a bipolar sequence with independent elements and with the same probability to appear for each. And then you need to find what's the amplitude of basis function in order to ensure you need energy, what's the autocorrelation of basis function, and after you need to find what's the autocorrelation function of the resulting signal S of 1 of t, and what's the power spectrum density. This is the general question for this task. And besides this, you also, no, not besides this, just in order to find this autocorrelation function, you do it in 2 steps. First, you calculate autocorrelation function for basis function itself, and another step, you need to calculate autocorrelation function for discrete sequence of delta pulses. So this is the main, and actually you have this flow for most of them, most of the tasks that provided. I mean, yes, we have nicer words there, but in general, idea is that you have something in the middle, autocorrelation or signal or power spectrum density, and then you need to find all the rest parameters. Okay, we have 15 minutes, and I think we have additional part. So let me check what we can do in this in minutes, unless there are more questions. Okay, maybe we can just try to solve another very simple task. Or maybe actually it's too simple. Yes, you see that actually all these tasks from previous exams, and they're not difficult. I mean, actually, you need even less time than for our regular tasks that we solve during our tutorial. But you should do it quite fast because you have only 2 hours, and typically you have 6 tasks with up to 7 subtasks in each. Okay, let's see. Let's try to find something interesting. Or maybe you have questions regarding materials we discussed previously in our tutorials. Then we can also try to discuss these questions. Okay, let's just solve a simple task. We don't have so much time for a difficult one. And we can just revise material. So we assume that we have the following periodic sequence. I think it's task number 4. And it's from 2013. So we have the following periodic signal. We have U0 times sum and goes from minus infinity to infinity. We have rectangular pulse, t minus capital T over 2, minus n times duration of one period, divided by capital T. We know that period equals to 3 times capital T. And we need to draw the signal y of t first of all. At the beginning, so let's say this is our period, 3 capital T, 0, let's say 6 capital T, and so on. So, and we have rectangular pulse at centered, or the first rectangular pulse for n equals to 0, centered at capital T over 2. And then we have 2 intervals with nothing. Then we have another pulse, and we can continue this sequence periodically. So we need to determine the first and the second moment of y of p of t. So this is how it looks like. And what was the amplitude? Amplitude was U0 for each pulse. And we need to find UP1 question mark and UP2 question mark. So how can we find first moment? It is nothing else as mean value integral from minus infinity to infinity of our signal over time. And we just need to calculate mean value. And for second moment, we calculate not just mean value, but we calculate mean value of squared, mean squared value. So we just simply take 2pt squared and then calculate integral. And if we look to our signal, we see that actually it's periodic. So we simply can consider only one interval. And what will be the value for this? What will be the mean value? It will be U0, or we can say it will be U0 times t divided by 3t. So we can say that it will be this amplitude times duration times t divided by the total duration that we have. Yeah, maybe then we should, 1 second, it will be t divided, yeah, I should modify correspondingly the expression. I should also modify it to be integral over t, yes, but then I should also divide by also divide by duration, by capital T. T, do we have, yeah, or we can simply write 3t. And for the second part, it's the same, but divided by 3t, by the total duration. As a result, we have u0 times t divided by 3t, and gives us that mean value will be u0 divided by 3. And for the second part, we calculate square value, and it will be u0 squared times duration capital T. And again, we divide by what's the duration of one period. It's 3t. As a result, second moment will be u0 squared divided by 3. So this is how it looks like. Okay, there is also a question if we should have negative part. Yes, of course, we should have a negative part, but yeah, I mean, I didn't show this negative part, but of course you have it. Of course, you also have negative part because your signal goes from minus infinity to infinity. Okay, if you want to have negative part, we can also introduce it. So we have 1, 2, 3, and then we have pulse at this position. It will be minus 3t, from minus 3t to minus 2t. Yeah. And of course, we also, if this sequence goes to minus infinity. Okay. What else for this task? So we have first and second moments, okay. And second, we need to find power stochasticity. Right. We know how to do this. I can copy our original signal. But again, in order to simplify our problem, we can do the following. We can represent our signal as u0 times rectangular pulse, t minus capital T over 2, divided by capital T, times, no, sorry, not times, but convolution with sequence of delta pulses, and goes from minus infinity to infinity. Delta pulse, t minus n tp. So this is how it looks like. Now we need to find the power stochasticity. And of course, when we want to calculate power stochasticity for such a problem, we need to, first of all, calculate Fourier transform for our signal itself to get spectrum. And then we need to find the squared value, model absolute value squared of this spectrum. So if we calculate spectrum for our signal, so, or we can also, it was first option, another option, you of course you can calculate autocorrelation function, and then you can calculate the Fourier transform from autocorrelation function. But let's calculate through, does ask us anything about, but they don't ask us about anything. I know they ask us about autocorrelation function after we calculate power stochasticity, and actually it's already implicitly tells you how you should calculate what's the way of calculating power stochasticity. So first we take our Fourier transform for our original signal. We get u0 times capital T times C function of pi f capital T times we have additional shift in time domain, exponential minus j2 pi f t over 2 times, and we have sequence of delta pulses. So after Fourier transform, we get 1 over Tp. Maybe we should write it as 3 capital T, duration of period, times summation mu goes from minus infinity to infinity, delta pulse, f minus mu 1 over 3 capital T. This is duration of period. And then we say that our parasitic density, nothing else as UP model squared. And we can, as a result, we can write it. Yeah, actually, we shouldn't forget about scalar. We have T and T we can cancel. And scalars that we have 1 over 3 and U0. So we get U0 over 3 squared times C square function pi f capital T times, and then we have this sequence of delta pulses. Mu goes from minus infinity to infinity, delta pulse f minus mu 1 over 3t. So this is our resulting parasitic density. And we can, yeah, as a final part for today, we can plot it, and it will be the end of our tutorial. Yeah, maybe I should use slightly different interval. So this interval corresponds to 1 over capital T, then 2 over capital T, minus 1 over capital T, minus 2 over capital T. And we need to plot C square function. C square function. And again, no, it's just envelope. It's just envelope, so let me show this dashed line. So this is envelope, and this envelope we use in order to scale the corresponding sequence of delta pulses. The maximum value of envelope will be used squared over 9, and delta pulses stands at or like distance between delta pulses equals to 1 over 3t. So the distance between two delta pulses, 1 over 3t. And this is how it looks like, how the resulting sequence of delta pulses looks. And yeah, that's all. This is what we have for our parasitic density. And I think I have specified everything what I need for this part. Okay, yeah. And next time we start discussion about, I think we start discussion about decision boundaries. And next time we have tutorial on Wednesday, next Wednesday. And for now, I'm planning to do tutorial online via WebEx, unless we get any additional information. But it will be next week. Okay, are there any questions for the materials that we discussed today? Can you explain 1 over 3t in Fourier transform? Yes, of course. I think you're talking about. I think you're talking about this part. It simply comes from definition of Fourier transform for delta pulses, because you remember that if you have Okay, we have original sequence of delta pulses. And we write it as delta t minus n3 capital T. This is original sequence. We have to modify it in order to match our expressions from basic Fourier transforms. We have to write it as 1 over 3t times 3t times summation n goes from minus infinity to infinity, delta t minus n 3 capital T. Then the expression which contains 3t and summation after Fourier transform can be written as summation mu goes from minus infinity to infinity, delta pulse f minus mu 1 over 3t. But we have additional scalar that left, and we have to place it in front of this expression 1 over 3t. This is the reason why we have 1 over 3t in our expression, because our period equals to 3t. If we would have different period, then we would have different scalar. And t also in front of psi comes from the Fourier transform of rectangular itself. Yeah, this is the reason. Okay, any other questions?
Sir, on this sinc function, this goes from minus infinity to infinity, right? And in the previous sinc as well.
Yes, yeah, I mean, always C function goes to infinity, but I don't show. Yeah, but you're right that it goes
Just for confirmation.
minus infinity to plus infinity. Yeah,
Okay.
it's absolutely right.
Okay.
Yes, other questions? Okay, if not, then I would like to say thank you for your attention and wish you a productive rest of the week, and see you next week. Goodbye.